Hi, everyone. I just wanted to take a moment and explain to you how you can use the periodic table and the connection with the periodic table to what we know about atomic structure and all of our discussion about ionization energy, because they all actually fit together in a extremely clever and beautiful way. Mendeleev would have been very proud had he known his periodic table would have lasted to this day and support what we know about quantum theory. So remember that we were talking about ionization energy, and ionization energy is the amount of energy it takes to remove this outermost ground state electron. Okay, so for hydrogen, the ground state electron is equal to 1, and that's also its valence electron. But in larger atoms, let's say neon or any other atom with more than one electron, the valence electrons will be farther from the nucleus, right? So that hopefully makes sense to you, that the valence electrons sometimes are in n is equal to 3 or n is equal to 4. Remember that as we get further away from the nucleus, right, the electron is less tightly held. So just think about that for a second, less tightly held. Why wouldn't it be strongly held? Why is it weakly held? Can you think of a reason why? Well, if you were thinking, well, the nucleus is positive and the electrons are negative, and so the closer the charges are together, there's going to be more force of attraction and electrostatic force holding them, and that's exactly right. So the closer the electron is to the nucleus, the more strongly it's held. The more strongly it's held, the more energy is going to be taken to rip it away. So if we plot our ionization energies on a graph, it looks something like this, and you saw that already. Well, where do the ionization energies come from? Well, actually on table 8 of your IB data table, or IB data booklet, has the first ionization energies, something called electron affinity, which we'll talk about later, and electronegativities, which we'll also talk about later. So you can see the first ionization energy is the number in the upper left-hand corner on this periodic table. So it actually has values, right, numerical values, because it's measured using different apparatus. But you can actually get a number for the SI units, it's in kilojoules per mole. Sometimes it's shown as electron volts, which is can be converted to joules as well. But if you take a look at hydrogen and what we know about hydrogen, we know that hydrogen has an electron configuration of 1s1. Remember that on the periodic table, this is the s block over here, the p block is over here. The D block is hidden right now underneath that, but that's all the transitions, and the F block is at the bottom. So hydrogen is 1s1. So you can see that we're filling the 1s orbital. And if you look at the ionization of energy of hydrogen, it's relatively high. It's not the highest on the periodic table, but it is relatively high. But then helium has a larger, much larger ionization energy right here. Okay, and if we think about that for a second in terms of our electron configurations, that would be a 1s2 electron configuration, and then that means the s orbital is filled, completely filled. So we have this peak at a completely filled orbital. We already knew that we've been told that when the orbital is filled, it has a special stability. And this is the evidence, this is the data that shows us that stability. It's stable because it's going to take a lot of energy to rip away that one electron in the 1s full orbital. And so that's how we know that it's stable and it has a special stability, because the data tells us that. If you continue on to lithium, if you think about the electron configuration of lithium, it would be 1s2, it's completely filled, and then it starts on the second period, so that represents the second shell, so n is equal to 2, and it's in the s block, so it's 2s1. so that's down here. Notice the huge drop in energy between the filled, the 1s orbital, and the really just starting to be filled 2s orbital. It's quite low in energy. So if you think about lithium atoms right here, you've already sort of considered when lithium atoms are ionized. That means that an electron, its valence electron, which is in the 2s orbital, can be removed fairly easily. So what happens when you remove an electron from lithium, its outermost electron from lithium? It now has an electron configuration that's isoelectronic with helium, this special stability state, right? It has the same full electron configuration. And it forms a lithium ion, which has a positive 1 charge. So that's why all of the elements we know in group 1 here create a +1, or very easily create a +1 ion. Because this energy, this ionization energy, is actually quite low. They easily lose it, right? It would take a lot more energy to try and gain it to have the same electron configuration as neon, right? It's a lot easier just to lose that electron, and it is energetically a lot easier. And so if we look at the electron configurations across the whole second period, n is equal to 2, from lithium to neon, we can see that there is a general increase, right? You can draw a straight line. However, there's these like weird little dips, right, happening at boron and oxygen. So let's just think about what's happening there. So we have lithium, so that would be 1s2, 2s1, and then beryllium would be 2s2. So now at 2s2, you should recognize that is a filled 2s orbital. It has this special stability state that is slightly higher, right? So that's why when it's at this high and you see the dip, that we're starting then to fill the next orbital energy, right? It's not up here. It's because this is filled that it has a special stability state. And then we start filling the 2p at boron. So boron goes 2p1, then that would be 2p2 and 2p3. If we think about 2p3, right, you should recognize that that is a half filled, right? We already know that 6 electrons can fit into the p orbital. That is the 2p orbital is half filled. Again, that's why you get this little peak and a little dip afterwards, because of that special stability state. Remember when you were making orbital diagrams, we wanted to divide the electrons each into one of the p orbitals, and that is why we have this special state, and that's where those exceptions to the electron configurations come in. And then you start with oxygen, so that would be 2p4, 2p5, and then at neon 2p6. And we know the 2p6 is completely filled. It has a noble gas configuration, electron configuration, because it's a noble gas, and it's high, very high ionization energy. That's because the 2p is now filled, and it's going to take a lot of energy to take away one of those electrons, right, to have a fluorine electron configuration. In fact, that's what we see does not happen. It doesn't happen very easily. Remember that fluorine really will gain electrons more easily, right, to get to this higher electron state. Fluorine is not going to make positive ions, right? It makes negative ions when it gains those electrons. So we have this beautiful, nicely filled, completely filled energy level with the 2p's at this high state. So the question is then, why is the 1s helium's electron configuration, or helium's ionization energy, higher than neon's? Can you think of a reason why? Well, right, again, because the valence electrons in neon, right, those 2p electrons are going to be further away from the nucleus. And so the forces of attraction is not going to be as great. And actually, there's 2 reasons for that. First of all, it's farther away. And so the force of attraction between the positive nucleus and those further electrons is going to be less. But also there's something, called the shielding effect. So those n is equal to 1 electrons actually shield the attractive force between the n is equal to 2 electrons and the nucleus. That's called the shielding effect, and you might come across that later. Well, I hope this has been helpful to you in understanding the ionization energy relationship with the graph of the trends in ionization energy and relating to our model.